height. Now we're going to move to a very specific case of linearly homogeneous function, which is a Cobb-Douglas production function. Okay, so in its general form, it looks like this. It's A, usually denoting state of technology or level of human capital, but let's call it state of technology. It's a constant, and then we've got K to the power alpha times L to the power beta. Okay, and look, first thing interesting about this type of function is that it's really easy to read its degree of homogeneity. Why? Look, if I'm going to take this function and I'm going to replace k with jk and L with JL, just like we always did in order to check for returns to scale or degree of homogeneity, we calculate that it is A times J alpha times K alpha times J beta times L beta. Or after simplification, we get that this is J to the power alpha plus beta times A power K alpha L beta, right? So we see that here we actually got Q. So we clearly see that this function is homogeneous, and we see the degree of homogeneity can be read from alpha plus beta. And look, it is really easy to see that if alpha plus beta is bigger than 0, we will have increasing returns to scale. Why? Because if I double the capital and double the labor, I will more than double level of production. So we call this increasing returns to scale. Oh, I'm sorry, of course, not 0, 1. Then, if alpha plus beta is equal to exactly 1, it means that if I double the capital, double the labor, I will double the production. We call it constant returns to scale. Okay, and finally, the last possibility, if it's below 1, we say we have decreasing returns to scale. And doubling the capital and doubling the labor will less than double the level of production. Okay, so we see that this function is clearly homogeneous, and then we can read very easily degree of this homogeneity as a sum of the two exponents. However, there is a second very nice property that actually explains why it is used in economics so often, and this is that this production function produces actually isopoints that are decreasing in convex, the way they should be in the analysis. Okay, but what is an isopoint? Isopoint is the counterpart of the indifference curve, however not used in consumption but in production. So from perspective of the company. The company can choose between combinations of labor and capital in order to produce certain level of production, right? Let's just say that a given company wants to produce Q0 output. And look, in order to do it, they can use different combinations of capital and labor. As it turns out, if everything is like under the assumptions of neoclassical economic model, we would expect the isoquants to look like this. And they actually are giving us efficient combinations of capital and labor that can be used in order to produce a certain amount of output, some Q0 unit. And look, it makes perfect sense. We can build, we can produce using more labor when we have labor-intensive technology. This is what we see over here. We use a lot of labor, little capital. When labor, for example, is very cheap, because wage is low. And here we would see capital-intensive technology when we use very little labor and a lot of capital. And of course, we got like every possibility in between. And look, the thing is, of course, it's harder and harder to substitute capital for labor, right? Or labor for capital. We see that here, each time when we drop by 1 unit of capital, we need to give more and more units of labor. Exactly the same scenario that we had in the case of indifference curve. So basically, isoquant is an indifference curve in the production space, so in the labor capital space. Okay, so we are actually going back to this very soon. However, at this moment, let's just prove that actually in the case of Cobb-Douglas production function, our isoquant will be downward sloping and convex. So what do we need to do? Look, our production level that we are trying to attain, given here, we will try to do it by, of course, using capital and labor. Okay, so now, out of this relationship, I need to calculate out the slope of the isoquant. Actually, it is done quite easily. First thing we need to do is to logarithmize this equation, right? And what happens when we do so? Each product will turn into a plus. Okay, let's do it in steps. So we will have ln A plus ln K alpha plus ln L beta equals ln Q. Right? Because logarithm of the product is the sum of two logarithms, right? The next thing I can do is to take those exponents in front of the logarithm, right? So I'm getting this is ln A plus alpha ln K plus beta ln L equals to ln Q. Okay. Look, in this context, again, the best way to deal with this situation is using implicit function rule, just like we did previously, as we will see. Okay, so first thing we want to do is that our function is going to be this equation. The only thing we need to do is to move ln Q0 to the other hand side of the equation. Now, what is the condition in the case of implicit function rule? Look, we're going to be looking for the derivative d k d l, right? Now, in order for us to be able to find this, first thing I need to do is to check the derivative of this equation with respect to k is actually different from 0. So I differentiate f with respect to k, and I'm getting that this is alpha over k. Capital is assumed to be positive. Alpha is a positive, usually a fraction, but not necessarily, but definitely a positive number. And we get that this is positive, different than 0. So we can use the implicit function rule. Okay, so the implicit function rule tells us that d, k, d, l should be equal to the negative of the derivative of function f with respect to l divided by the derivative of function f with respect to k. Okay, so let's find those two derivatives. They're very easy to find. Here we're going to have beta over, on the top we're going to have beta over l, and in the bottom we're going to have alpha over k. Or we're going to have that this is negative beta over alpha, if I'm not mistaken, beta over alpha times k over l, or capital to labor ratio, right? Or lowercase k. Now, we know that all three of those components are positive. We've got minus up front. From this, we get that the isoquant that is going to be produced by this production function is definitely going to be a downward sloping function. Then, in order to assume whether it says whether this is concave or convex, we need to calculate the second derivative. So in this case, we're just going to simply calculate the derivative of this. Right? Okay, so we get that this is going to be the derivative of negative beta over alpha k over l, and that's it. Okay, now in this case, we see that those are constants, right? We can take them out of the derivative. And look, all we need to differentiate now is k over l. And look, it might seem tempting to just treat k as a constant. However, we need to remember that we cannot do it. Look, here we are actually having a function that ties ln k and ln l to, or k and l to one another, to only those that can produce u0, right? So here actually what we need to do is that we need to use quotient rule. Again, quotient rule is giving us that this is negative beta over alpha times 1 over L squared, right? And inside, we're going to have what we would have on the top, right? So first, derivative of the first expression times the second expression, so we would have here L times d k d L, right? Derivative of the expression on the top times the expression at the bottom. And now, minus expression at the top minus times the derivative of expression at the bottom, which would be 1. And if I'm not mistaken, this is gonna be it. Yeah. Okay, so we need to now assess the sign of this. Well, we clearly see that here we have plenty of positive expressions, right? So this is positive. Capital is positive, but it has a minus up front, right? And if capital has a minus up front, it means that this is negative. Now, this expression over here is negative because we know it from, we just assessed it, times something positive, it is negative. So look, we know that this entire expression is negative, right? Times expression that is, this entire expression is negative. Times expression that is positive gives us minus, and minus in front, so everything is positive. And because the second derivative is positive, we can be sure that the function is convex, so the isoplot has this nice shape that we are used to from textbook economic models. Okay, so we know now main characteristic of the Cobb-Douglas production function. However, as usual, there is, even in this very strict category of functions, there is one that has a special place, and we're going to concentrate on it a little bit more. This is, of course, the case where we have linear homogenic, right? This we usually write this case as Q equals to A times K to the power of alpha times L to the power 1 minus alpha. Those two sum up to 1, so we clearly see that actually degree of homogeneity is 1. So look, if this is a linearly homogeneous function, let's check if everything that we actually said before will work out, right? So all the properties of this linearly homogeneous function, whether it do work in here or not. Okay, so let's start by rewriting this function into the capital labor ratio. Look, for example, I can rewrite this as A times K to the power alpha times L to the power negative alpha times L, right? So, those two can be put together, and we get capital over labor to the power of alpha times L, and this is a new function that we get over here. That is a function of capital alone, capital labor ratio alone, and L is simply at the end the way it should be, right? So now we know that we can do it. Now, will we get the same results for average products? So we start with average physical product of labor. So we take the production level and we divide it by L. And look, from this we can right away see that what we get is A K to the power of alpha, which is a function of capital to labor ratio alone again. Okay, so now we can calculate average physical product of capital. So we divide level of production by capital, and we get that this is A L divided by Q times A k alpha, right? Because we have L at the top, we divide by k, so we get 1 over capital labor ratio in the bottom and 1 over k alpha over here. And this is like k to the power negative 1, so we can write it as a lowercase k to the power alpha minus 1. So again, property works. So maybe now we can check the very same thing for marginal products. So we remember that marginal physical product of capital is given by partial derivative of q with respect to capital. So if I differentiate this expression with respect to capital, I get alpha a k to the power alpha minus 1 times L to the power 1 minus alpha. Right? But look, if I'm going to take minus out of this exponent, I'm going to get that this is alpha times a k to the power alpha minus 1 times L to the power negative alpha minus 1. So again, I can combine those two expressions together, and we get that this is alpha a k over L to the power alpha minus 1, or alpha a lowercase k to the power alpha minus 1, which is a function of capital to labor ratio alone. Okay, then we go to marginal physical product of labor. Now I differentiate this function with respect to labor, and I get out of this 1 minus alpha times ak to k to the power of alpha times L to the power negative alpha. And look, I can bind those two right away. So I'm getting 1 minus alpha a k over L to the power of alpha, or 1 minus alpha k a k to the power of alpha, which is a function of a capital to labor ratio alone. Okay, so look, the only one last thing we need to do over here is to make sure about the property number 3. So Euler's theorem. So we have here that k times marginal physical product of capital plus labor times marginal physical product of labor should give us output. Okay, so let's check it. So I put here k, and this is my marginal product of capital here. So I get that this is k times alpha times a k alpha minus 1. And then I add L and times 1 minus alpha to the power a k alpha. And look, we could solve this problem in various different ways. The easiest way, I think, is to simply try to get rid out of the production function that we have out of the all of these expressions. And let's do it. So we take out L times a k to the power of alpha. That's it. Okay, and let's see what we're going to have in parentheses. Look, out of this, we're going to have, if I taken out of this L, right? It's like I need to now multiply this by 1 over L, right? Then alpha stays over here. I've taken out a, and I've taken k to the power of of alpha, so I'm left with lowercase k to the power -1. But look, those three expressions are products, right? That we multiply them. This is capital to labor ratio. So if I have capital to labor ratio times 1 over capital to labor ratio, I see that the only thing I'm left with is alpha. Okay, good. And look, here there is no problem, because if I'm going to take AK alpha times L, all I'm going to be left with is 1 minus alpha. However, as we can notice over here, we are left with alpha here. That cancels each other with alpha here. So we are left with just 1. Which means that we have now proven that Euler's relation works. There is one more thing we should discuss about the Cobb-Douglas production function in this special case. Look, according to Euler's theorem, we've got that K times marginal product of capital, so spending on capital in the production process. In the long run, we remember marginal product of capital is being paid under competition is paid to the capital. So this is how much we pay for the capital, so the red rate, and this is how much capital we use. This is spending on capital. We know that then if we add to this, we have the same for labor, how much we spend on labor, how many units of labor we use, how much we pay for the unit according to its marginal product, and this is equal to Q. Now look, if I divide both sides of this equation by Q, I'm going to get two expressions that sum up to 1 very nicely, and they have very nice economic interpretation. This is the share of the product that is going to capital, right? Because this is how much has been spent on capital out of the entire production, and here we have how much that it goes to workers, to labor. So look, if we would have 0.6 here and 0.4 here, it means that 60% of the production is going to the capital and 40% to labor. Remember that this is a long-run equilibrium, so all the product is distributed, entire product is distributed between labor and capital. Okay, now look, this has a very nice interpretation of how to calculate. As it turns out, again, we don't have to calculate it. All we need to do is to look at this function appropriately. Why? Look, let us calculate this expression. Let's start with capital. So look, a capital share. So look, I can take and substitute directly from here, right? And this is capital times alpha times A times capital labor ratio to the power alpha minus 1, all divided by Q, and Q is L times A K to the power alpha, right? So, what can we do with this? Look, we see that definitely A's are canceling each other out. However, we also see that capital labor ratio to the power alpha and capital labor ratio to the power alpha are canceling each other over here. So what we got left is capital to labor ratio times alpha times capital to labor ratio to the power -1. Well, then when we multiply those two by each other, they turn into 1 and we've got alpha. And look, this makes, of course, for a very nice result. Because alpha in this scenario is actually telling us on the share of the product that is going to a given factor of production. And look, we can right away calculate, oh, it doesn't require that much calculation, that of course L must be equal to 1 minus alpha, right? However, let's check it in a similar fashion. Here we've got expression for 1 minus alpha A K alpha. We divide it by L A K alpha. And here, actually, the situation is even simpler. We see L's canceling each other out. We see A's canceling each other out. And capital to labor ratios to the power of alpha canceling each other out. So we get 1 minus alpha. So look, Cobb-Douglas production function in general has this very nice property. But just by looking at it, you can know what is the degree of the homogeneity of a given function, right? However, we also see that in the context of production function, it has another very nice property because it's actually telling us what is the share of the product going to each of the factors of production. Okay, so this is it about Cobb-Douglas production function. In the next couple of videos, we're gonna learn how producers optimizes by minimizing the cost given some level of production, and we can put the knowledge we got over here to more applicable use. See you in the next video. Take care.